Hi everyone, welcome to my channel. Now in this video I am going to solve a few problems from the chapter Mechanical Properties of Solids. These are the NCERT book problems. So the first problem, it reads a steel wire of length 4.7 meter and cross-sectional area 3 into 10 power minus 7 meter square stretches by same amount as a copper wire of length 3.5 meter and cross-sectional area 4 into 10 power minus 5 meter square under a given load. So what is the ratio of the Young's modulus of the steel to that of the copper wire? So let's see how to proceed about this question. So in the question, what are all the information given? Length of steel wire, it is given to be 4.7 meter. Okay, and area of steel wire, it is given to be 3 into 10 power minus 5 meter square. Okay, now length of copper wire, it is given to be 3.5 meter and its area is given to be 4 into 10 power minus 5 meter square. Now it is also given that for a given load, the stretching in steel and copper both are same. So that means F and delta L same for both. Same for both steel and copper. Okay. Now Young's modulus, we have to find the ratio of the Young's modulus. We are asked to find the ratio of the Young's modulus. So Young's modulus steel to Young's modulus copper. This ratio is to be found. Okay. Now we know that Young's modulus, it is ratio of longitudinal stress to longitudinal strain. Stress is force per unit area. This is restoring force per unit area, and this is change in length by original length. Now under normal condition, we know that the restoring force is equal to the deforming force or the load. So this is the expression for Young's modulus. So here it will be, so since F and delta L both are same for steel and copper, now this Young's modulus expression can be written as FL by A delta L. Now since F and delta L are same, so this quantity and this quantity, they are same for both. Okay, so this implies F and delta L is constant. So in that case, Young's modulus, it is proportional to length, directly proportional to length, inversely proportional to area from this expression. So Young's modulus of steel by Young's modulus of copper, it will be length of steel by length of copper multiplied by area of copper divided by, this is A. So this is area of copper divided by area of steel. Now if we substitute the values, this is 4.7 into 4 into 10 power minus 4 divided by length of copper 3.5 into area of steel 3 into 10 power minus 5. So if you calculate these values, then you will get the required answer to be 1.79 or approximately 1.8. Okay, so this is how you have to proceed. So this is solution to problem number 9.1. Now next question is based on a graph. This graph, so this is a graph between stress and strain. Okay, now 9.2 question reads that we have to find from this graph, you have to find the Young's modulus and approximate yield strength. Okay, now Young's modulus, it is the ratio of stress to strain. So for stress 150, the strain is 0.002. So for solution to 9.2, Young's modulus, it is ratio of stress by strain. Okay, so now from this graph, corresponding to stress 150, the strain is 0.002. So it is 150 divided by 0.002. Okay, so if you can simplify this, you will get 7.5 into 10 power 10 Newton per meter square. Now the other question they have asked is to find the value of the yield strength. Now yield strength, it is, see, the linear part, the proportional limit. Beyond the proportional limit we have the yield strength, that is the stress corresponding to this point. So that is somewhere around 300 into 10 power 6. This side scale is multiplied by 10 power 6. So yield strength, it will be how much? It will be 300 into 10 power 6, or I can write it to be 3 into 10 power 8 Newton per meter square. Okay, Newton per meter square. So this is 9.2. Now next question, 9.3. It is also a graph based question. Solution to 9.3. Again a graph based question. So this is the stress strain graph for two materials, material A and material B. Now they have asked which of the materials has a greater Young's modulus. Okay, Young's modulus, it is a ratio of stress and strain. Okay, so that means the slope of this graph. So as you can see, the slope for stress by strain, for this part, the slope is greater than that of B. So that means Young's modulus of this material A will be greater than that of material B. Now then they have asked which of the two is a stronger material. Okay, now stronger material is, again, see, for this material B, plastic region is very small, so fracture point is very close to the elastic limit, whereas for this fracture point is very far away from the elastic limit. So that means again material A will be much stronger than that of material B. So this is answer to question number 9.3. Then you have this question 9.4. You have to read the following two statements below carefully and state with reasons if it is true or false. The Young's modulus of rubber is greater than that of steel. Okay, now see, so this is 9.4. 9.3 we have already solved, so this is 9.4. See, Young's modulus, it is FL, load into length, divided by area into change in length. So if other quantities are constant, then that means Young's modulus is inversely proportional to delta L. Okay, now for a given load, the extension in, suppose you have a rubber wire, this is a rubber wire and an identical steel wire. Okay, now suppose they have same length and cross sectional area, and both the wires, rubber wire and steel wire, they are subjected with the same load. Now if they are subjected to the same load, the change in length for rubber will be far greater than that of steel. So this quantity for rubber will be greater than that of steel. The Young's modulus is inversely proportional to delta L. So that means Young's modulus for rubber will be far smaller because delta L is large. This is inversely proportional. So this gives Young's modulus of steel will be far greater than that of rubber. Okay, so for Young's modulus of steel will be far greater than that of rubber. Okay, then next question is the stretching of coil is determined by shear modulus. Yes, it is not. Stretching of a coil is determined by shear modulus. You may think, some may think, not you, but some may think that it is not shear modulus, it is Young's modulus, because there is increase in length. See, this is the spring. Okay, now when it is stretched, what happens? there's a change in the shape. There's a change in shape. Okay, so that change in shape is measured in terms of modulus of rigidity. So this is stretching of coil is an example of shear modulus. Okay, so these are the solutions to the first 4 questions of the chapter mechanical properties of solids.